right, turn it over now to Dio, who will talk about the work in rapid certifiable trust.
Thank you. We are there? Perfect, thank you. So, well, good afternoon. I'm going to be presenting our results on the rapid certifiable trust. Basically, the problem we are going after is actually the adoption of new technologies in the DoD, right? But of course, adopting new technology also requires to have a validation of this new technology. In particular, we are very interested in finding out, of course, that we will get the capability problems by this technology, but on top of that, it's very important that the mission is not compromised because of misbehavior of these systems, right? And this gets complicated by two factors. The first one, we already heard about AI, machine learning. We already heard that machine learning allows us to adapt to the environment as we execute, but it also means that we do not know the final behavior at the same time. So that's a huge challenge for us, right? The second thing is the cyber-physical systems, like most systems in the field are today, are systems, software systems that interact with the physical environment, right? So this means that we need to react to the physical environment. We need to react and provide the correct actions at the right time before we actually crash, for instance, right? So that's very important. So it means we not only need to verify these actions, but the timing as well. And of course, this is composed by, we need this fast. Everybody's saying, yeah, we need this fast, right? We say we need to be very certain that we are going to be safe, but if you are safe and you don't do it fast, it's useless, right? So we need to go after that. Clearly, there's a lot of interest in the DoD as signaled by the different rapid capability offices in the different services. So we are trying to go after that. We really want to go and kind of provide services for that, right? So it means we need to be fast, but we need to be trustworthy as well. And with all the complications that we discussed on machine learning, on cyber-physical systems, and it means that we not only need to go after the two things that I already discussed, timing and logic, but also the physics. How do we know that the physics that we are modeling actually really works? And this is actually what rapid certifiable trust is all about, right? We go after fast, trustworthy validation, and the core technology we use is automation of formal verification. But the problem there is complexity. Right? So we have a technology that is very thorough, but this technology do not scale. Traditional formal verification do not scale, so that's a huge problem that we have and that we are kind of taking over, right? And the second thing, as we discussed, is this adaptive behavior, right? So what do we do? So what we do is we use a specific technique approach that we have that we call enforcement-based verification. So the key about this verification is do not verify. So what do we mean? So the idea is to leave as many components as possible not verified. But then to do that, we add small pieces of code called enforcers that will keep monitoring the unverified components and watch for potentially unsafe actions, outputs, right? And if we discover such an output, then we will replace the actions for safe ones. And of course, then what we do after that, we verify these enforcers. So the end result is that the whole system will be able to be verified for particular properties, right? As just limiting our verification to these enforcers. Clearly, when we talk about this verification, because these are applied in cyber-physical systems, that verification needs to be based on logic, the correct values, timing at the right time, and matching the expected behavior in the physical environment, right? The last piece we do is to say, well, okay, so we already verified these components, but what if they get attacked? Or an error actually in the unverified components actually modifies the trusted component. Therefore, we need actually to protect this against these kind of events. Okay, so let's go to the math. Well, don't worry about this. I will just explain the high-level picture. This is part of the results we have from the control side of things, from the physics modeling point of view. There are just a few things that are important to look in this slide. One is to say the way to think about the physical behavior of things Of course, we model this with kind of differential equations and everything. But the idea is that we model the behavior. I guess we don't have a pointer. Well, we model the behavior in a way that we see how the system behaves and identify a safe region of behavior, if you will, and also, let's see, enforceable region. So in a way, if we discover that we are experiencing an unsafe behavior because of the unverified components, then we are able to catch this behavior before it leaves the safety region. And catching means the enforcer kicks in, then takes over the control of the system and brings it back to the safe region and towards the set point that we have, right? The technique used for this is called Lyapunov functions, and the idea of the way to think about it is that we model this as a cone, right? Where at the bottom of the cone, that I cannot point to, I guess. At the bottom of the cone is a set point, is a safe zone, and if the unsafe behavior moves the system within any place in this cone, we can still drive it down to the bottom of the cone, right? So that's the way to think about it. Of course, there's a lot of math involved, but that's the way to simplify, to have a simplified view of this. And then, well, that's only for a single set point. So if you think of a drone, we have been playing this with drone examples, right? Is that the drone kind of staying stationary in one position, that will be the set point. But then we need to drive it through a mission. So we connect these multiple set points, and then we verify the safe transition between one set point and the next one. And that connection actually is the one that will drive us to a safe mission, if you will, right? So then we can now formally verify a system that has a lot of components that are not verified, but has one small piece that is the enforcer that actually ensures that the Lyapunov function is preserved, right? And that can drive us from one cone, if you will, to another cone safely. We have, of course, proofs of such safety, but also we have proofs of liveness, at least initial liveness, so it's not fast enough. You will see this in a moment, but that's part of our initial steps to go forward. Oh, there you go. So I mentioned this drone. So this drone is modeled in our particular modeling technique with, of course, a lot of equations. And you can see kind of the trajectory of the drone in this graph that we have there. It's a 3D graph. But in this graph, you also see that there is a drop in the trajectory. That drop actually is an attack, right? This is basically an error. And then the error was kind of provoked by some unsafe behavior from an unverified component. And then the enforcer will catch this behavior and return it safely to the set point and to continue the trajectory. So now we will see a simple video that hopefully I'm going to be able to. Where do I do this? Oh, there you go. So you will see the same trajectory that you already saw in the graph, but this is with the real simulation. Unfortunately, this is a hardware-in-the-loop simulation. I'll tell you what happened with the real drone in a moment. That everybody laughs because we know. Okay, here we go. So you will see that it will start going up a little bit. It's slow, but it's the way we are running this example. This was in an example that we applied in another project. And you were able to see how that dropped. The enforcer captured the behavior, returned it to the set point, and then continue the mission. So the question is like, yeah, maybe we're done. Well, the problem is that we only verify the physics, right? We only verify the physics. Actually, this is a physics verification of real code running. It's real code running in a Raspberry Pi that is controlling actually the simulation. But in reality, we need to go also after trust. So I mentioned before, right, that we not only need to verify a component, but we need to protect it from potential modifications to the code, right? So what kind of protection do we need? So let's take a look. Now, this is another point of view of the same software. The software will be receiving some sensing, the position of the drone, and doing some actuation, movement of the drone, right? And this is a typical way to see the general controller. Clearly, if we have a bug, right, if there is some error in our code, this output can be compromised, may not be the correct one, right? And we saw that in the particular example that I presented before. And so what do we do? As I mentioned before, what we do is we add an enforcer. So we do not trust this blue component, but we trust the green component because we verify the component. So it means that it will be receiving the output from the untrusted component, check whether it's safe or unsafe, and then it will do something about it. We will provide the correct one. But then the question is, do we really trust it? What happens if that is modified? And that's exactly what we were talking about. So one, in this guy is modified, of course, we can now go back to the wrong behavior. And that is the problem that we are trying to address. So in order to take care of that, we actually use protection, memory protection. We protect this piece of code in order to avoid modifications, and therefore, now we can really trust that the output that will come out of this component actually will be correct based on our verification property, right? So for us, trusted means is both verified and protected. Maybe we are done. Well, not exactly. We just protected the value, but we have not protected the timing. We can still get an late output, which is very dangerous because, of course, we can crash. If we don't break on time, we can crash. So this is kind of a modified view of this system. And in this view, you can see, well, we have the protection, but this is periodic. So this is the way all these controllers work, periodically sampling the environment and doing corrections, right? So this is the multiple periodic activations. And what can happen is that if we see that one of the untrusted components was attacked, maybe we can protect the value, but this particular component can enlarge the execution time, maybe get into an infinite loop and never produce an output. So it means in the end, it can produce an output late. So even though we can trust the memory, we can trust the value of the enforcer, we cannot trust the timing. So what do we do if we cannot trust the timing? So what we do is we ask Amit to help us. We create inside this hypervisor a set of trusted timers, actually, to really guard the timing, the output of our components in such a way that we will have a small activation guarding that we see an output. We see an output here, so we don't do anything. We see an output here, we don't do anything. And once we get there and say there is no output, then we will be able to issue a default action that will be safe, right? So we need to prove that that will be safe. For instance, for the drone, could we just hover while we discover what is going on, right? So now we create a composite here. So the composite is, there is a piece that executes periodically that is trusted from the value point of view, but not trusted from the temporal point of view. And we added this layer, the layer from the hypervisor, the verified hypervisor, that actually is guarding the timing. And this, now we have a trusted memory, trusted value, and the trusted timing as well, right? So this is what we call the mixed trust task. So it's a task. You can think this as a thread that is executing periodically that has memory protection, but also has timing protection. Of course, this, as I mentioned before, is implemented inside the verified hypervisor, verified in the Intel, to be verified in the ARM processors. And this is actually what we did. We have two schedulers actually working side by side, one in the hypervisor and the other in the virtual machine. They are coordinated, but one of the challenges of this coordination was to be able to prevent dependencies from the hypervisor coming from the virtual machine, because virtual machine is not trusted. There was a bit of a challenge to kind of set up the protocol to make it, to avoid kind of inverted trust links. Clearly, once we have these two schedulers, now we need to develop the equations to find out what is the worst case response time and figure out whether we can guarantee the deadlines we are looking for. Okay, so what do we have so far then? So we have some physics verification, as I showed before. This is based on the Sliapanov analysis that we have. We have temporal verification with the guaranteed timing, even in the presence of bugs and attacks. We are able to protect actually our enforcer both from the value and space point of view and the temporal point of view. And the logical verification with the hypervisor that we already discussed. There's a lot of more details about the Uber Spark framework that we don't have time to discuss actually. We have some demos. I mentioned that we have the code for the drone based on open source. This is actually very interesting because open source is everywhere. I mean, even for instance, we have seen DoD systems that use the GNU compiler, right? GNU compiler is open source, right? So it's a big problem and we need to deal with that, right? We have the hardware in the loop. That's actually what I presented. We have coded in a DIY drone. So the funny thing is that what happened recently is that we verify a lot, but we forgot to verify one component, that is the battery. So the battery exploded in the hand of one of our researchers. That was something that we were not expecting to be verifying, but I guess we need to at least have some additional safety concerns that we need to address. Right? We have this real-time mixed trust framework already implemented in Raspberry Pi, ready to run when we recovered all this, and this mixed trust scheduler as well. Number of publications, these are 3 of them. 2 more are under submission. So the road ahead. One of the challenges we have had for some time, and this is one of the things that you probably already observed in our demo, is that sometimes when you're trying to have absolute guarantees, then you have some problems with performance. So that's one of the challenges that we are going after. We want to find ways to quantify and verify the long-term mission performance. There are some ideas we are exploring already with signal temporal logic to do this. We want to do this cross-domain optimization. For instance, one of the things we are doing right now is developing new control systems, because from the control point of view, you can tolerate some deadline misses. That's fine, but the problem is that what is the tolerance? How many of these deadlines I can miss? This is one of the questions that we are investigating, how to find the best optimization of these combinations, if you will. And of course, assumptions of multiple enforcers working together will have assumptions that can contradict each other. And that's one of the things we are working on as well. From a transition point of view, we have multiple views. I show the video of one of the applications into one of the ONR projects that we have here. The idea is that we are trying to at least transition part of these verification techniques into a Navy system. And we'll see whether this kind of has a positive evaluation that they can be adopted, at least part of these techniques into a real next refresh of a Navy system. We're exploring other applications for the CPS, other CPS defense systems like MDA, and of course in autonomous systems. Right? Part of our experiments with drones is to be able to explore autonomous systems and how we can have a better applications whenever the system is doing some learning in the middle. Right? This is our team. We have most of these are from our own SEI team, and 3 of them from external campus and also Washington University, St. Louis. And with this, I think I'll be happy to take questions. This is coming. Thank you.
Thank you. So the Boeing 737 MAX MCAS was an enforcer system.
Yes, correct.
And as my understanding is there were no software bugs in it.
Right. I mean, I would say verification, what is the word I want to use? do not prevent policy errors or human errors, if you will, from that point of view, right? So there are multiple explanations for that particular incident. Some of them talking about they were not using kind of the dual redundancy sensor that they have.
Single sensor failure.
The pilots were not trained properly. So, I mean, of course, what you say was the property formally verified violated, maybe not, but we don't know, right? Because in the end, it was not formally verified to start with, right? But yes, I mean, it's a bigger scope, and it's an important scope to take into account.
So we've been talking about this. This is kind of a homunculus over your system, and you can think of a homunculus above your homunculus.
Yes,
right?
correct.
It's homunculi all the way up, right?
So for instance, there was one of the articles that I like, that it was very interesting, was comparing the philosophy between Airbus and Boeing, right? So in Boeing, the philosophy has been, according to that article, always the last resource is the pilot. And Airbus changed that long time ago. They say, no, we will trust the machine and we need to make the machine trustworthy, completely trustworthy, right? So I think the addition of this mechanism kind of violated the philosophy of the Boeing, and they didn't, I don't know. We don't know enough details about that, but it's a real risk. That is correct. Yes, sure. Yeah.
Yeah, maybe this is also a question for Amit. You mentioned verification. So for timing verification, did you mean total order plus meeting all deadlines under the assumption of sufficient scheduler? All of these?
Right. I guess the timing part will be my realm, and then I'll let Amit add to that, if you will. From the timing point of view, we talk about ensuring that the task will finish before the deadline, even if they have multiple interruptions and interleavings from other tasks. Now, the total order will have to do with ordering of events. We do not see events as part of that. The only thing for which we see events as part of the equation, if you will, is whenever they coordinate the two schedulers together, right? So for that, we have some sort of a sketch of a proof, and we are working on a formal proof in a time automata. Make sense?
Yeah, the timed automata is actually the sort of preferred approach when you try to compose with the logical verification of the hypervisor itself. Because when you do memory safety or memory integrity and the logical correctness of the hypervisor, the timed automata approach sort of fits into that realm of sort of pre-post, condition validation and so on. So that's one sort of promising approach that you're investigating, but we are not discounting other approaches. And in the long term, such timing verification, and this is again stemming from our initial sort of discussions and realizations, such timing verification might require support from the underlying hardware in terms of timing contracts or ISA contracts. So the instruction set needs to say, okay, I'm going to complete in X clock cycles, and that's a post condition that I'm giving you. It's not, and it's not going to be done anytime soon, because the notion of timing verification to an accuracy of clock cycles and missed deadlines is a hard problem. Yeah, it's a. Oh no, it is in progress, and as I said, it'll inform some of the hardware nature, hopefully. Yeah.
Probably time for one quick question, if anybody has one. Okay.
Thank you.